these cosmic detonations. Supernovae also generate powerful neutrino bursts, subatomic particles that barely interact with matter. The detection of neutrinos from SN 1987A in the Large Magellanic Cloud confirmed key theories about stellar collapse and provided rare direct observational data on the inner workings of a dying star. Some supernovae challenge our understanding of stellar physics. Hypernovae, for instance, are even more energetic than regular supernovae and may be linked to long-duration gamma-ray bursts, the most intense explosions in the universe. The nature of so-called superluminous supernovae, which shine 10 times brighter than ordinary supernovae, remains an active area of research. Another mystery is the fate of Betelgeuse, a red supergiant in the Orion constellation. This massive star is nearing the end of its life and could explode in the next few thousand years, or even tomorrow. If it does, it will be visible in broad daylight from Earth, offering humanity a front-row seat to one of the most extraordinary cosmic events. Supernovae not only illuminate the past but also shape the future of astrophysics. Scientists are using advanced simulations, high-energy observatories, and gravitational wave detectors to probe the secrets of these stellar cataclysms. Understanding supernovae could help answer fundamental questions about the nature of matter, the origins of elements, and the ultimate fate of the universe. The next nearby supernova could revolutionize our understanding of the cosmos. Telescopes worldwide are constantly scanning the sky, hoping to catch the next great stellar explosion in real time. When it happens, astronomers will be ready. Supernovae are also responsible for some of the most extreme and mysterious phenomena in the universe, including magnetars. Magnetars are highly magnetized neutron stars, with magnetic fields trillions of times stronger than Earth's. These bizarre remnants occasionally release powerful bursts of X-rays and gamma rays, capable of affecting our planet's upper atmosphere even from thousands of light-years away. The origin of magnetars is still debated, but many scientists believe they are born from the most energetic core collapse supernovae. Another intriguing class of stellar explosions is the so-called failed supernova. In these rare cases, a massive star collapses directly into a black hole without producing a visible explosion. Some astronomers have observed stars that seem to vanish without a trace, hinting that direct collapse black hole formation might be more common than previously thought. If confirmed, this could reshape our understanding of how black holes form and evolve. Supernovae are not only natural laboratories for studying high-energy physics, but they also play a role in shaping entire galaxies. When a supernova explodes, it injects vast amounts of energy into the surrounding interstellar medium. This feedback process can regulate star formation by either compressing gas clouds to trigger new star birth or dispersing gas and preventing further star formation. In extreme cases, multiple supernovae can create superbubbles, vast cavities in galaxies filled with hot, ionized gas. The Milky Way itself has been shaped by countless supernovae over billions of years. Some astronomers suspect that past supernova explosions may have influenced the evolution of life on Earth. The hypothesis of a supernova-induced mass extinction suggests that cosmic rays from a nearby explosion could have altered Earth's atmosphere, leading to climate change or increased mutation rates. While no definitive evidence links a supernova to past extinctions, isotopic traces of iron-60 found in deep-sea sediments suggest that at least one supernova occurred relatively close to Earth within the last few million years. The search for supernovae extends beyond our own galaxy. Astronomers regularly discover and analyze supernovae in distant galaxies, using powerful telescopes like the James Webb Space Telescope. These extragalactic supernovae provide crucial data for understanding the early universe, as they offer glimpses into the lives and deaths of the first generations of stars. Some of the earliest supernovae may have contributed to the reionization of the universe, a period when the first stars and galaxies transformed the cosmos from a dark, neutral state into the bright, structured universe we see today. The interplay between supernovae and cosmic rays is another fascinating area of research. Supernova remnants, like the famous Tycho and Cassiopeia A remnants, are believed to be primary accelerators of cosmic rays, high-energy particles that travel near the speed of light. When these charged particles collide with the interstellar medium, they produce gamma rays, which can be detected by space telescopes. Understanding the origins of cosmic rays could shed light on some of the most energetic processes in the universe. In recent years, astronomers have begun using machine learning and artificial intelligence to detect and classify supernovae more efficiently. Automated surveys like the Zwicky Transient Facility, ZTF, and the upcoming Legacy Survey of Space and Time, LSST, are expected to discover thousands of new supernovae every year. These vast datasets will help refine theoretical models and potentially uncover new, exotic types of stellar explosions that defy current classification. Another breakthrough in supernova studies came with the advent of gravitational wave astronomy. When two neutron stars collide, a process often initiated by a supernova, they produce both a visible explosion, called a kilonova, and gravitational waves, ripples in spacetime first predicted by Einstein. The detection of gravitational waves from the neutron-star merger GW170817 confirmed that kilonovae are responsible for creating heavy elements like gold and platinum, solving a long-standing astrophysical mystery. As technology advances, astronomers hope to capture a supernova in the earliest stages of its explosion, something that has rarely been observed in real time. Supernova early warning systems, which monitor nearby stars for pre-explosion activity, may soon allow scientists to predict and study these stellar deaths as they unfold. If successful, such efforts could provide unprecedented insights into the final moments of massive stars. Even in death, supernovae continue to shape the universe in ways we are only beginning to understand. Their explosive legacies live on in the stars that form from their remnants, in the elements that compose planets and life itself, and in the mysteries they leave for future generations to explore. Supernovae are not just violent endings, they are also cosmic rebirths, setting the stage for the next generation of stars, planets, and even life. The elements forged in these titanic explosions, carbon, oxygen, silicon, iron, and countless others, become the building blocks of everything we see around us. Every atom in our bodies heavier than hydrogen and helium was, at some point, created in the heart of a massive star and released into space by a supernova. In this sense, we are all made of stardust. One of the most enigmatic consequences of supernovae is the creation of exotic objects like quark stars, a hypothetical state of matter even denser than neutron stars. Some physicists speculate that under extreme pressure, neutrons in a collapsed star could break down into their constituent quarks, forming an incredibly compact remnant. While no confirmed quark stars have been observed, ongoing studies of unusually massive neutron stars suggest that these strange objects might exist. Supernovae are also responsible for some of the most luminous transient events in the cosmos. One such phenomenon is the Perrin stability supernova, a rare explosion that occurs in extremely massive stars, at least 150 times the mass of the Sun. Unlike typical core-collapse supernovae, which leave behind a remnant, parent-stability supernovae completely annihilate the star, leaving no black hole or neutron star behind. These colossal explosions were likely more common in the early universe when massive first-generation stars dominated. Another fascinating class of explosions is the so-called zombie or repeating supernova. Some supernovae, like the peculiar IPTF-14HLS, have defied expectations by exploding multiple times over several years instead of fading away. This challenges existing models of stellar death and suggests that some massive stars may undergo prolonged, episodic eruptions before finally collapsing for good. Supernova remnants, though often associated with destruction, can also be sites of intense astrophysical activity. Pulsar wind nebulae, for instance, form when a rapidly spinning neutron star, or pulsar, injects high-energy particles into its surrounding environment. One of the most famous examples is the Crab Nebula, which houses a central pulsar that rotates 30 times per second, emitting beams of radiation that sweep across space like a cosmic lighthouse. The effects of supernovae extend far beyond their immediate surroundings. Some researchers believe that the cosmic rays generated by supernovae may have influenced Earth's climate over geological timescales. The hypothesis, known as the cosmic ray climate connection, suggests that variations in supernova activity in our galactic neighborhood could affect cloud formation and, consequently, global temperatures. If true, this would mean that the history of life on Earth has been subtly shaped by distant stellar explosions. From a technological standpoint, the study of supernovae has led to innovations that extend beyond astrophysics. The techniques developed to detect and analyze supernovae, such as advanced image processing, machine learning, and high-energy particle detection, have applications in medical imaging, nuclear physics, and even materials science. The hunt for neutrinos from supernovae has also inspired the construction of massive underground detectors, which are now used for monitoring nuclear activity and searching for rare particle interactions. Looking forward, astronomers are eagerly anticipating the next nearby supernova, as it would provide an unprecedented opportunity to study these cosmic explosions up close. Some candidates, like Betelgeuse and Eta Carinae, are closely monitored for signs of impending collapse.